Okay, the first thing, I spoke to the IT people, and they are going to increase your limitations, but don't abuse them.
Like how much?
I don't know.
Good job, Doha.
And for the first, okay, we spoke this in the session today, and also I put an exam 1 study guide and on the web page. What? Okay, do you hear me now? Come to the front row now. Okay, it's on the web page. And we spoke this in the session, and the first page is what is exam 1 going to cover. So these are the topics. And then on the next page you will see that the topics and the problems that you will see in the exam. So this can, in the exam, the problems will be coming from here. And if you are downloading the class lectures that we distribute after each class, and you will see that everything is in the slides. Okay? And the other thing, you can download the exams from last year or from the previous year and just print them and bring it to the exam. That should help. Okay? And the other issue is I distributed some of the quizzes in the morning, and I will continue to do on Monday and on Wednesday. And most of you were not happy with the results, with the zeros. Well, we'll find a solution, but I mean the quiz is the objective of the quiz is to drive you insane, okay? So just do your best and study, okay? But for sure, I think in the syllabus it says we are going to drop some of the zeros in the quizzes. So we will do that. And there will be like 25 at least quizzes in the end, okay? And the percentage is 10%. So that shouldn't really matter. Okay, so let's continue what we are doing. On Wednesday, we started the solution of diffusivity equation. So if you remember the diffusivity equation, we are solving for the pressure. And the pressure is a function of time and radius. And then what we were doing to make things easier, we were converting the parameters in the diffusivity equation into dimensionless parameters. So when you do that, you end up with the dimensionless form. So now you have the dimensionless pressure, and the dimensionless pressure is in terms of the dimensionless radius, if you have a radial flow system, or in terms of dimensionless time. And how are we solving the diffusivity equation? This is a second order partial differential equation. Okay, we have to impose conditions, right? First, we have to assume an initial condition, okay? And the second is two boundary conditions. And what are the boundary conditions? Yeah, and the inner boundary condition is either constant rate at the wellbore or constant pressure at the wellbore. And the other boundary condition is infinite acting reservoir, or you can assume a closed reservoir, or there might be a constant pressure at your boundary. And the initial condition was always initial pressure. Well, in the case of water in flux, you have a continuous pressure support, right? So it's the pressure at the boundary is always constant if you have water in flux. So we are doing this for mathematical convenience. So our initial condition in terms of dimensionless parameters was 0, and the inner boundary condition is -1 if you assume a constant rate. And if you remember, we are obtaining this using the Darcy's law. And here is the definition of the dimensionless pressure. And we are obtaining this again using Darcy's law and using the inner and outer boundary conditions and also the initial condition. And we were obtaining the dimensionless time and the dimensionless radius by intuition. And if you solve it, and then if you assume a line source, then this will be your solution. And the solution in terms of radius and dimensionless radius and time is given in terms of the exponential integral function. And this is the derivative of it. And as we told, so this becomes negligible when time increases. So you will see that the derivative will be a constant. But this is not the derivative actually. This is called the well-testing derivative. This is when you take the derivative and multiply it by time. And this is how we are approximating the exponential integral. And here is the mathematical definition for the exponential integral function. And today we are going to use this expression and then solve for the pressure relation in a drawdown or build-up test. Okay, so let's start. Okay, the first thing I am going to do, I'm going to take the solution here, and then I will say that I can approximate the exponential integral by this formula. Okay, up to here, I'm using the mathematical properties of the natural logarithm function. So the first thing, we are trying to obtain the solution at the wellbore. So at the wellbore, this term equals to 1, right? So this means that in our solution, pressure will be a function of time. Okay, did you write this part? I'm going to delete it. What? No, x is not equal to RD square. X is here. This is your x. Yep. Yeah, gamma is called Euler's constant, so it's equal to 0.577, and it continues. The definition of RD is R over RW, right? And we are looking for the solution at the Valbor. So R is equal to RW and RD is equal to 1. What? Sorry, I can't hear you.
Where'd the 1/2 go?
1/2? Oh, okay. Thanks. Yeah. Okay, now this is our solution approximated by the natural logarithm. And what we are going to do next is we are going to use the definitions of the dimensionless parameters and then insert them into this equation. Okay? And so did you remember this? Okay. No, it's 2s. Yeah, because I took it in the denominator. Okay, did you write this? I'm going to the next page. Okay, good to see that you are following. Okay, so now I am going to insert the definitions of the dimensionless parameters. So the first thing will be case here. Okay, so I can write this as
So that's ln of d, not ln of n.
ln t, yeah. Yes. Yeah. Okay, do you remember the values for PDC and TDC? They are constants. And for PDC for field units is equal to 1 over 141.2. One over 141.2. I think it's in the slides. And TDC is equal to 0.0002637. Well, just keep it as TDC, then you will insert it. I mean, it's 0.0002637. I should write down that. Yeah, according to the field units.
Okay.
I mean, if it's Darcy units, yeah. Yep. Yeah, this will be flowing pressure, yes. Well, it's in hours. I mean, if you are using hours, it's yes, yes. But in our equation, if you are using field units, T is in hours, P is in pressure, P is in PSI, and K is millidarcy. What else? R in foot. Okay, did you write this down? Okay, the next thing is we have to convert the logarithms into, we have to convert the natural logarithms into logarithm which is based on tan. So why are we doing that? Because we are always going to plot the pressure versus the logarithm. And the logarithm will be based on tan. There is no way we can plot ln. Okay? And there is a relation for that. And it is so once you see ln in this equation, then you will substitute this with the logarithm. Okay, just keep this in mind. Okay, now I'm going to the next page. Did you write this down? Okay. Okay, once you do that, and then plug the definitions of the logarithm, and do the calculations, this will be your solution. And if you recall from the previous equation, we had constants there. So these are all related to those constants, and this is also a constant. Okay, now tell me what this equation looks like when you plot this on a plot. Okay, deleting. Okay, so this is the solution of the diffusivity equation, assuming a line source solution. Our inner boundary condition is the constant rate. Okay, and we are assuming an infinite acting reservoir. So our variable is time, and we are going to compute the pressure. So the pressure is changing with respect to time. So this equation, is it a straight line or is it logarithm? Yeah, that's correct. So let's draw it. Okay, now tell me the derivative of the pressure equation now. Okay, I am taking the derivative. So if you take the derivative of a constant, it's 0. Right? And what was the definition of our well-testing derivative? It is equal to So now you are looking at a very important result, because so this is the pressure versus time. And this is the well-testing derivative versus time. So when you have the pressure data, and then you take the derivative of your pressure data, and if the data seem constant on the plot, then what you understand? No. Yeah, correct. Okay, repeat. Okay. When you plot the well-testing derivative of the pressure with respect to logarithm of time, and if it seems like if it seems constant, And then you understand that you are in the infinite acting radial flow region. Hmm? You want me to repeat? Up and down? Well, you mean in... I don't understand. I mean, if you mean the derivative data goes up, well, it can be in Malbor storage in several other flow regimes. But the important thing is, during the infinite acting radial flow, the derivative is constant. That's the point. And the value of the constant is B over ln tan, right? So this is the MSL in the equation here. So this is the definition for the MSL. This is the slope of the straight line. So once you obtain the slope, then you know Q, right? You know B, you know viscosity, you know the thickness. So from the slope, what you find is the permeability of the reservoir. Okay, do you want me to repeat? Okay, did you get this? What you are going to do is you will have the pressure data, okay? And then you will plot your pressure data versus time. And then if it shows a straight line, then you will understand that you will be in the infinite acting radial flow. And the other way is you will plot your derivative with respect to logarithm of time. And if it shows a constant, then you are in the infinite acting radial flow. And the value of the constant is the MSL. And from the MSL, the slope of the straight line, you will find the permeability. Okay, the other thing is, so what if t goes to 1? So this term is 0, right? And what is this term? This is the intercept of the straight line, right? So you are looking at the intercept and tell me what you can find from the intercept. No, we already found k from the slope. No, we already know it. We know the initial pressure. We already know this. We know this. Yeah. Okay, so two important conclusions. From the slope we find permeability. From the intercept we find the skin factor. Okay, so this is what will happen. We will have the pressure data, and this data, when you plot the pressure data, it will look like a straight line during infinite acting radial flow. And what you are going to do, okay, let's give numbers, 0.01, 0.1. Okay, so where is the infinite acting radial flow regime? Okay, tell me. When you see the straight line, then you are in infinite acting radial flow, okay? And then what you are going to do, you know that in the infinite acting radial flow, it's a straight line, so you are going to fit this part of the data with a straight line. Is there a ruler? Okay, the points are data, the line is your model. So what is the slope? No, slope is just MSL. Okay. And you will find the slope of this straight line, okay? And where is the intercept? Is it here? Yes? That's correct, because the intercept at And the intercept will be here, 1. And you will read the value of this. And this is called P1 hour in the equation you already saw. It can be Valborg storage or some other things. It can be Valborg storage or some other things, but it's not related to our discussion now. It can be anything, but when you see data show a straight line behavior, then you are in the infinite technical gradient flow. And the most common mistake I've seen so far, people are reading the value of P1 hour of they are coming up with this point as P1 hour. It's not correct. You will always read the slope and the intercept from your model, not data. Data guides you or shows you if you are in infinite acting radial flow or if you are in a pseudo steady state flow regime, if you are in Valborg storage regime. It shows you that, but what you are going to do, you understand the flow regimes, and then let's say if you are in infinite acting radial flow, then it should be a straight line. So this is our straight line here. And then this will be the value of the intercept. So always read from the model, not the data. So the MSL gives you the permeability value, and the P1 hour, the intercept, gives you the skin factor. Okay? And these solutions are for pressure drawdown tests. And we will see how they look like for the build-up case next week. Yeah, but we haven't seen it yet. Valborg search? I don't know. Also, we can say in the infinite acting radial flow, we find the permeability and the skin factor. And when you are in the Valborg storage flow, when you are in Valborg storage flow regime, you find the value of the Valborg storage coefficient. But if you are in the infinite acting radial flow regime, then you find the value of the permeability and skin factor. And if you are in pseudo steady state flow regime, what can you obtain? You obtain the area or volume. So each flow regime you can obtain different things. Okay, in the Valborg storage flow regime, you find the value of the Valborg storage coefficient only because you are producing only from the Valborg, right? And when you are in the infinite acting flow regime, then you are in reservoir and you find the value of permeability and you find the value of the skin factor. And when you are in the pseudo steady state flow regime, you can find the value of the area or volume. Steady state? You don't see steady state. Yeah.
Why would you need to know the local storage coefficient? What does that help you with?
Well, it can help you when the Valborg storage effects are going to be diminished.
But wouldn't you just see that in a straight line?
Yeah, we will see that next week. I mean, when you are in the Valborg storage flow regime, the pressure and the pressure derivative will be identical. So that way you understand that you are in the valve storage domination.
So you just have to know what you're out of.
Yeah. Also, it doesn't make any sense. It doesn't make any sense to find the value of the valve storage coefficient. It's just the important thing is to your permeability, skin factor, and the area. Okay, are there any more questions? Yep. Okay, in the pseudo-steady state, if you plot the pressure versus time, not the logarithm of time, it shows you a straight line. Okay, if there are no more questions, then it's over.